Tonight, we are going to talk about why humans still have not reached Mars. Not because Mars is impossible to see, not because we do not know where it is, and not because rockets cannot cross the distance. The problem is that Mars is not one challenge. It is a chain. First, a crew has to leave Earth for months, exposed to radiation and weightlessness. Then, they have to land a vehicle far heavier than anything we have ever landed there. After that, they must survive on a frozen desert with thin air, toxic dust, delayed communication, limited supplies, and no quick rescue. Every step has to work because Mars is too far away for a second chance. That is what makes this story so strange. We have sent robots there for decades. We have driven rovers across its surface. We have made oxygen from its atmosphere. But sending humans is not the same mission with people added. It is a completely different kind of problem. Before we begin tonight's journey, subscribe to the channel if you want more calm space documentaries like this. Leave a like if you enjoy slow journeys through the universe, and write in the comments where you are watching from, and what time it is where you are right now. It is strange to think that people are listening from different parts of one small planet, while Mars waits far away in the same sky. Tonight, you are watching the Just About Space channel, talking about why humans still haven't reached Mars. Mars has always had a strange way of feeling close. It is not close in the way the moon is close. No human being can look at Mars and imagine reaching it in a few days. No rescue ship could simply leave Earth, arrive quickly, and bring a crew home if something went wrong. Mars is a moving world on the other side of interplanetary space, and most of the time, it is separated from us by a distance so large that ordinary language starts to fail. Yet somehow, it feels familiar. We have seen its deserts in color. We have watched dust devils move across its plains. We have photographed frost, dunes, cliffs, craters, ancient riverbeds, polar caps, and rocks sitting under a pale orange sky. Rovers have driven across it slowly, meter by meter, as if Mars were already part of our extended neighborhood. Orbiters have mapped it in detail. Landers have listened to its wind. Instruments have drilled, scooped, tasted, measured, and searched. For many people, Mars no longer feels like a point of light. It feels like a place. That is what makes the question so frustrating. If we know where it is, if we have already landed machines there, if the maps are real and the photographs are real, then why has no human being ever stood on that surface? The simple answer is that robots are easier. A rover does not need to breathe. It does not get scared inside a metal cabin after months away from Earth. It does not lose bone density in microgravity, or need surgery, or argue with its crew, or panic when a seal begins to leak. A rover can freeze, shut down, restart, fail slowly, and still be considered a useful mission if it sends enough data before the end. A human mission cannot be treated that way. The moment people are added, Mars stops being a destination and becomes a survival system. The spacecraft cannot be only a vehicle. It has to become a temporary world. It needs air, water, food, power, communication, radiation protection, waste systems, medical tools, spare parts, navigation, exercise equipment, fire safety, software that does not fail at the wrong moment, and enough redundancy that one broken valve does not become a death sentence. Then, after the journey, the crew still has to land. And after the landing, they have to live. And after living there, they have to leave. That is the part many simple versions of Mars exploration skip. Reaching Mars is not the same as sending a camera there. It is not even the same as sending a very expensive robot. For a human crew, success means arriving alive, staying healthy enough to work, surviving the planet's surface, launching again, crossing space a second time, and returning to Earth. Anything less is not the mission most space agencies are trying to build. This is why Mars has remained both near and unreachable. It is close enough to tempt us, close enough to send machines, close enough to imagine boot prints in red dust, but it is far enough away that every mistake becomes heavier. Every kilogram matters. Every medical risk becomes more serious. Every delay in communication reminds the crew that Earth is no longer a place that can help in real time. A moon mission is dangerous, but the moon is still part of Earth's neighborhood. Apollo astronauts could reach it in days. Radio conversations had only a small delay if a mission had to end early. The path home was frightening, but physically short compared with Mars. The moon gave humanity a first step away from home, but it did not demand that a crew live as an isolated planet for years. Mars demands something different. It asks whether humans can carry enough of Earth with them to survive without Earth. That is the real reason the planet remains untouched by human feet. It is not because one rocket is missing. It is not because nobody wants to go. It is not because Mars is impossible in the fantasy sense, as if the universe has placed a wall around it. The obstacle is more practical and more unforgiving. Every part of the chain has to work. Launch from Earth has to work. The spacecraft has to work for months in deep space. Radiation protection has to be good enough. The crew's bodies have to remain strong enough. The navigation has to hit a moving target. The landing system has to bring a heavy vehicle through a thin atmosphere. The habitat has to keep people alive on a frozen desert. The surface systems have to survive dust, cold, and wear. The return vehicle has to launch from Mars. The trip home has to work. Earth re-entry has to work. Mars is not one problem. It is a stack of problems balanced on top of one another. That is why the progress can look strange from the outside. We can drive a rover on Mars and still not be ready to send people. We can make oxygen from the Martian atmosphere in a small technology demonstration and still not have a full system that can support a crew. We can test habitats on Earth, train astronauts in isolation, study radiation, and build larger rockets, while still being honest that a real human Mars mission is not simply waiting for one final switch. The machines already there are not proof that humans should have arrived easily. They are proof of how hard Mars is, even before humans are included. A rover can land far from perfect and still continue. A human lander cannot tumble across a plane and call it a successful arrival. A rover can spend a cold night conserving power. A crew needs a controlled environment. A rover can die alone. A crew must come home, or at least have systems strong enough that survival is not based on luck. That difference is the heart of the story. We have reached Mars many times with machines, but we have not yet reached it with a living bubble of Earth. The bubble is the hard part. Imagine shrinking the basic needs of a human world into a spacecraft. Air has to be cleaned and recycled. Water has to be conserved. Food has to last or be produced. Carbon dioxide has to be removed. Temperature has to be controlled. Waste has to be managed. Microbes have to be understood. Fires have to be prevented. Because fire in a sealed spacecraft is not just fire, it is an attack on the atmosphere the crew is breathing. Now move that sealed world away from Earth. Put it outside the strongest protection of Earth's magnetic field for months. Place it on a trajectory where turning around may not be simple. Fill the space around it with radiation that cannot be seen. Let the crew live with the knowledge that every sound from the spacecraft matters. A pump, a fan, a valve, a warning tone, a vibration in the structure. On Earth, a technical problem can become an inconvenience. On the way to Mars, an inconvenience can become the beginning of a survival problem. All of this is still before the first boot touches Mars. That fact alone explains why the timeline is so difficult. People often ask why we have not gone yet, as if the delay is proof of a hidden reason. But the visible reasons are already severe enough. Human Mars exploration sits at the intersection of almost every hard problem in spaceflight: propulsion, life support, radiation biology, landing physics, power systems, robotics, medicine, autonomy, psychology, and planetary science. Solving one part does not solve the mission. A powerful rocket does not solve radiation. Radiation shielding does not solve landing. Landing does not solve food. Food does not solve return fuel. Return fuel does not solve medical emergencies. Mars forces every solution to connect to every other solution. Add shielding, and the spacecraft gets heavier. Make the spacecraft heavier, and launch becomes harder. Launch more mass, and the mission becomes more expensive and complex. Use less shielding, and the health risk rises. Stay longer on the surface, and the crew needs more supplies. Stay shorter, and the orbital timing may not allow it easily. Every choice pulls on the rest of the design. That is why Mars is not only a place. Mars is a test of systems thinking. Mars offers almost none of that. The air is too thin, and mostly carbon dioxide. Liquid water is not available in open lakes or rivers on the surface. The pressure is far too low for an unprotected human body. The cold is extreme. Radiation reaches the surface more easily than on Earth. The soil and dust may create chemical and mechanical problems. Even if there are useful resources, those resources have to be found, extracted, processed, stored, and protected by machines that cannot rely on a repair shop down the road. To live on Mars, humans have to bring the environment with them or build it from hostile ingredients. That is not impossible. But it is not simple. A mission can be 99% successful and still fail if the 1% is the wrong system at the wrong time. That is the brutal difference between inspiration and execution. Inspiration gets us to the design table. Execution has to keep people alive when Earth is only a small blue star behind them. This does not mean humans will never reach Mars. The important point is the opposite. The obstacles are not magical. They are real, physical, measurable problems. Engineers can work on them. Doctors can study them. Astronauts can train for them. Robots can test pieces of the answer before people arrive. The Moon can become a proving ground for equipment, habitats, operations, and human endurance beyond low Earth orbit. Mars is hard because it is real, not because it is fictional. That is what makes it worth understanding carefully. A fake explanation would say we have not gone because of one secret, one missing engine, one political decision, or one hidden truth. The better explanation is less dramatic and much more powerful. We have not gone because a human Mars mission is one of the most complicated chains ever imagined, and every link has to survive a place that is too far away for comfort. The first link is distance. Before radiation, before landing, before dust storms, before habitats and return rockets, Mars challenges us simply by not staying where we want it to be. It moves. Earth moves. The gap between them stretches and shrinks. The journey has to be timed to the dance of two planets around the Sun. So the next part of the story begins not on the surface of Mars, but in the empty space between worlds, where the red planet stops being a familiar photograph and becomes a moving target millions of miles away. That moving target is the part people often underestimate. Mars feels close because we have seen it so many times. Rovers have crossed its plains. Orbiters have mapped its canyons. Images from the surface show rocks, dust, hills, clouds, frost, sunsets, and a horizon that almost looks like a desert on Earth, with the color drained out of it. Familiarity creates a dangerous illusion. It makes Mars feel reachable, in the same way a mountain feels reachable when you can see it from a road. The destination is visible, so the mind quietly removes the distance. A red point in the night sky becomes a place. A place becomes a goal. A goal begins to feel like something waiting just beyond the next engineering push. But Mars is not a fixed island across calm water. It is another planet moving around the Sun on its own orbit, while Earth moves on a different orbit inside it. Sometimes the two worlds are relatively close. Sometimes they are on opposite sides of the solar system, separated not only by distance, but by the Sun itself. The path between them is never the same road twice. That is why a Mars mission cannot simply leave whenever the crew feels ready. Timing is part of the vehicle. To travel efficiently, mission planners wait for launch windows, periods when Earth and Mars are arranged in a way that lets a spacecraft leave one orbit around the Sun and meet the other planet later. The spacecraft does not fly in a straight line, like an arrow aimed at a target painted on a wall. It follows a curved path through the Sun's gravity, leaving Earth from one moving platform and intercepting Mars at a future position. You do not aim at where Mars is. You aim at where Mars will be. That sounds simple until you remember what has to ride along with the spacecraft. Not just instruments, not just cameras and wheels, people, water, air, food, radiation shielding, tools, medical supplies, spare parts, waste systems, navigation systems, engines, power, software, backup plans for the backups. Every kilogram matters, because every kilogram has to be pushed away from Earth, guided through deep space, slowed or captured near Mars, and eventually supported in a place where nothing can be bought, repaired, or replaced quickly. The Moon spoiled us in one important way. It taught the public to think of space travel as something that can happen within days. Apollo crews could reach the Moon in roughly 3 days. That was still dangerous beyond anything ordinary life can prepare someone for. But in mission terms, it was close. The Earth remained large in the sky. Radio conversations were almost real-time. If something went wrong, the crew and mission control were still operating inside a short chain of response. Apollo 13 was terrifying, but the damaged spacecraft was still close enough that improvisation, ground support, and a fast return path could work together. Mars changes that logic completely. A human Mars crew would spend months in transit. Depending on the trajectory and mission design, the trip is usually described in the range of many months, not days. NASA discussions often talk about journeys on the order of 7 to 9 months for traditional mission paths. Faster routes may be possible in principle, but speed is not free. More speed usually demands more energy, more propellant, more mass, more cost, or more risk somewhere else in the architecture. Spaceflight is full of trades. Make the trip shorter, and the rocket problem can grow. Carry more shielding, and the mass problem grows. Bring more supplies, and the launch problem grows. Reduce mass, and the survival margin shrinks. Mars punishes simple answers because every improvement pulls on another part of the system. For a robotic spacecraft, a long cruise is inconvenient. Engineers monitor it. They send course corrections. They wait. If the probe fails, the loss is painful, expensive, and scientifically disappointing. But nobody suffocates inside it. For a crew, the cruise is not just the road to the mission. The cruise is the mission. The habitat has to keep working day after day in deep space. The water recycling system cannot become an occasional convenience. It becomes survival. Carbon dioxide removal cannot be a background system people only notice during maintenance. It becomes a daily barrier between breathing and poisoning. Food storage, waste handling, exercise equipment, radiation monitoring, fire safety, mental health, navigation, communications, and power all have to function while the spacecraft is no longer near Earth and not yet near Mars. A journey to Mars is not like sitting in an aircraft for longer than usual. It is more like leaving one planet inside a small machine and asking that machine to become a temporary world. Distance makes that temporary world lonely in a way the moon never was. When astronauts speak from the moon, the delay is short enough that conversation still feels like conversation. From Mars, communication becomes something else. Radio signals travel at the speed of light, and even light needs minutes to cross the gap. Depending on where the planets are, a one-way message can take several minutes, and in some configurations more than 20 minutes. A question sent from Mars may not be heard on Earth until long after it is spoken. The answer may not return until almost an hour has passed in the worst back-and-forth cases. That delay sounds like an inconvenience until you imagine an emergency. A warning light appears. Pressure drops in a module. A crew member shows strange medical symptoms. A pump begins making a sound nobody expected. On the International Space Station, astronauts can talk with ground teams quickly. Specialists can watch data, give step-by-step guidance, compare the problem with past failures, and help the crew work through procedures in real time. The station is still isolated and dangerous, but it is tied closely to Earth by communications, logistics, and proximity. Mars cuts that tie thin. Mission Control cannot speak over an astronaut's shoulder while the crisis unfolds. By the time the ground understands the first description, the crew may already have had to act. The answer from Earth may arrive after the situation has changed. Instructions that would be useful in low Earth orbit could become too late in deep space. This forces a different kind of crew. They cannot only be pilots, engineers, scientists, and explorers. They have to become a small independent operations team, able to diagnose problems, weigh risks, perform repairs, and sometimes make irreversible decisions without waiting for permission. The farther they go, the more Earth becomes an advisor rather than a direct controller. Mars does not forgive the phrase "we can send it later." Later may mean the next launch window. That window is another hidden problem. Earth and Mars line up favorably roughly every 26 months. Miss a window, and the mission may wait years, not weeks. This affects launches from Earth, cargo deliveries, pre-positioned supplies, return vehicles, and mission architecture. Mars missions have to think in planetary rhythm. The calendar is not set by human convenience. It is set by celestial mechanics. And once the crew leaves, the timing continues to matter. A Mars mission is not usually designed as a quick visit with an immediate return. The planets move while the astronauts are traveling and while they are on the surface. Depending on the mission design, crews may need to stay on Mars for a long duration before a favorable return path opens. That means the landing is not the finish line. It begins a period of waiting, working, surviving, and preparing for departure when orbital mechanics allows it. The distance to Mars is therefore not just the distance going there. It is the distance that controls when you can leave Earth, how long you travel, how long you stay, when you can come home, and how much independence the crew must have through the entire journey. This is why comparing Mars with the Moon can be misleading. The Moon is a nearby world orbiting Earth. Mars is another planet orbiting the Sun. The Moon is days away. Mars is months away. The Moon lets Earth remain a direct partner in the mission. Mars forces Earth to become a distant base of support. A Mars mission crosses a threshold where the crew begins to carry home with them. That changes everything about risk. When a system fails near Earth, options exist. Maybe a rescue vehicle can be launched. Maybe the crew can return quickly. Maybe ground teams can walk astronauts through a repair in real time. For Mars, rescue becomes almost a philosophical word. A crew, in transit or on the surface, cannot expect another ship to arrive quickly if something goes wrong. Their survival depends on what was already planned, already launched, already landed, or already carried with them. Distance turns preparation into destiny. Every mission to Mars, robotic or human, is a bet placed months in advance. The spacecraft must arrive where Mars will be. The communication system must work across a changing gap. The power system must last through the cruise. The navigation must be accurate enough that a tiny error early does not grow into a missed planet later. For humans, each of those requirements is multiplied by the needs of living bodies. That simple difference forces the entire architecture to become more conservative, more redundant, and more complex. It also makes the journey heavier, because survival takes mass. More mass requires more launch energy. More launch energy may require assembly, refueling, multiple launches, or new systems. Again, Mars turns one problem into several. The distance problem is not solved only by crossing it once. We have already crossed it with machines many times. The question is whether we can cross it with a living crew, keep them healthy through the crossing, land them with enough strength and supplies to work, support them while Earth is minutes away by light and months away by transport, then bring them back through the same deep gap again. By itself, distance already explains why Mars belongs to a different class of exploration. It stretches time, it delays speech, it limits rescue, it locks missions to launch windows, it makes supplies finite. It turns every system on board into something closer to life support for a small moving world. And yet, distance is only the beginning. The space between Earth and Mars is not empty in the way the word empty sounds. It is open, but not harmless. It is filled with sunlight, charged particles, solar storms, and high-energy radiation from beyond the solar system. Earth protects us from much of that with its magnetic field and atmosphere. A crew on the way to Mars would leave most of that protection behind. So after the problem of distance comes the first invisible wall waiting inside that distance. Radiation. The distance between Earth and Mars is not empty. That may sound obvious, because space is never truly empty. There are particles, magnetic fields, dust, sunlight, and the long reach of the solar wind. But for a human mission, the most important thing filling that distance is something astronauts cannot see, cannot smell, and cannot simply avoid by closing a hatch. Radiation. On Earth, the word can feel abstract. It belongs to hospitals, power plants, warning signs, and numbers most people never have to think about. In spaceflight, it becomes part of the weather. Not weather made of clouds and pressure systems, but weather made of charged particles and high-energy nuclei moving through space with enough energy to pass through spacecraft walls, equipment, and human tissue. That is the invisible wall between Earth and Mars. It is not a wall that stops the rocket. The rocket can cross it. Robotic spacecraft have crossed it many times. Probes, orbiters, landers, and rovers have traveled through interplanetary space and reached Mars. But robots are much easier to send through radiation than people, because robots do not develop cancer decades later. Robots do not have bone marrow, eyes, brains, immune systems, or children waiting for them to come home. A machine can be hardened. A human body has to be protected. That difference changes the mission. As long as astronauts remain close to Earth, they are not completely outside protection. The International Space Station is in low Earth orbit, and even there radiation is a serious issue. Astronauts receive more radiation than people on the ground. They are monitored, their mission durations are tracked, and their exposure matters. But low Earth orbit still sits partly inside Earth's magnetic environment. Our planet's magnetic field and atmosphere form a shield that bends or absorbs many of the particles coming from the Sun and from deep space. A crew going to Mars leaves that shelter behind. Once they are on the long interplanetary path, the spacecraft becomes their main protection. There is no thick atmosphere around them. No planetary magnetic field wrapping the vehicle like a hidden umbrella. No hospital down the road. No quick return if a major solar storm erupts at the wrong time. The journey itself becomes a radiation environment. Two main kinds of radiation matter most for this story. The first comes from the sun. Solar particle events can happen when the sun releases bursts of energetic particles into space, often associated with solar flares and coronal mass ejections. The sun is not a constant lamp. It is a magnetic star, with storms, eruptions, and cycles of activity. Most of the time, astronauts can operate within planned limits. But a large solar particle event can raise the radiation danger quickly, and a crew outside Earth's magnetic protection would need a safe place to take shelter. This is the kind of threat mission designers can plan for in a specific way. A Mars spacecraft may include a storm shelter, a small region with extra shielding where the crew could retreat during a dangerous solar event. The shielding might include water, supplies, equipment, or dedicated materials arranged around the shelter. That idea is practical because solar particle events often involve particles that can be reduced with enough shielding, especially if the crew can move into the protected zone during the worst hours. But the shelter is not a full solution to all radiation. It is more like a bunker for a storm. The second kind of radiation is harder: galactic cosmic rays. These do not come mainly from the sun. They come from outside the solar system, accelerated by powerful events such as supernova remnants and other high-energy processes across the galaxy. They include protons, helium nuclei, and heavier atomic nuclei moving at enormous energies. Some of the heavier nuclei are especially concerning because they carry high charge and high energy. When they pass through human tissue, they can leave dense tracks of ionization, damaging cells in ways that are difficult to predict perfectly. Galactic cosmic rays are not usually sudden like a solar storm. They are more like a background rain, a slow, constant, high-energy drizzle through deep space. That makes them difficult in a different way. You cannot simply wait them out for a few hours. During the months to Mars, the exposure accumulates. During the surface stay, it continues because Mars has only a thin atmosphere and no global magnetic field like Earth's. During the return trip, it continues again. A crewed Mars mission is not one radiation event. It is months and months of exposure stacked together. This is where simple solutions become complicated. Add more shielding and radiation goes down. That sounds easy until mass enters the story. Every kilogram added to a spacecraft has to be launched from Earth, accelerated out of Earth's gravity, sent toward Mars, and supported by the rest of the mission architecture. In spaceflight, mass is not just weight. It is fuel, cost, engineering complexity, and risk. Shielding also behaves differently depending on the radiation type. For some solar particles, extra material helps strongly. For galactic cosmic rays, especially the most energetic heavy particles, shielding is much harder. A high-energy particle can strike the shielding material and create secondary particles, a spray of radiation produced inside the very material meant to protect the crew. That does not mean shielding is useless. It means shielding has to be designed carefully with the right materials and realistic models. More mass is not always a simple answer. A thick metal wall may stop some threats and create new complications with others. Hydrogen-rich materials, water, polyethylene, food stores, and waste products may all be useful in certain shielding strategies because mission planners already have to carry or manage them. The spacecraft can become a puzzle where survival supplies are also arranged as radiation protection. Even then, the risk does not become zero. NASA treats space radiation as one of the major human hazards for deep space exploration because it can affect long-term cancer risk, the central nervous system, the cardiovascular system, and other biological systems. It can also affect electronics, which matters because a Mars spacecraft depends on computers, sensors, communication, navigation, power systems, and life support. Radiation is not only a medical problem, it is a mission reliability problem. A particle that damages the wrong component at the wrong time can become an engineering emergency. A particle that damages tissue may become a health problem years later. Both matter, but they matter on different clocks. That is what makes radiation so difficult for storytelling. It does not always behave like a dramatic villain. It may not strike the crew with one visible blow. It may raise probabilities. It may increase risk. It may damage cells quietly. It may force mission planners to decide what level of danger is acceptable for a journey no human has ever made. On Earth, risk can be hidden because the planet is forgiving. On the way to Mars, the crew is inside a small vehicle surrounded by a radiation environment that cannot be turned off. This is why the word "still" in the title matters. Why humans still have not reached Mars is not only a question of ambition, it is a question of whether we can keep astronauts healthy enough through a mission that may last years from launch to return. A fast trip reduces exposure, but faster trips demand more energy. Better shielding reduces exposure, but adds mass. Different mission timings change the solar environment, but solar activity also changes the mix of risks. The mission has to be designed around trade-offs. More shielding means more mass. A shorter trip may reduce exposure, but it demands more energy. A storm shelter can protect against intense solar events, but it cannot become the crew's home for the entire journey. No single choice removes the problem. Every answer pushes pressure somewhere else. The radiation environment also shapes the surface mission. Mars is not as exposed as empty space, because its thin atmosphere does absorb some radiation, and the planet itself blocks half the sky below the crew. But compared with Earth, Mars is poorly protected. There is no thick atmospheric blanket and no global magnetic field. A habitat on Mars may need regolith shielding, meaning dirt piled over or around structures. Crews may need to limit surface time, plan extravehicular activity around solar conditions, and shelter during storms. That means the radiation wall does not end when the spacecraft lands. It follows the astronauts down. The first human footprints on Mars may be made inside suits designed not just for pressure and oxygen, but for radiation exposure, dust protection, thermal control, mobility, and emergency survival. The habitat behind them may look like a base, but part of its job would be to become a cave, a place where the crew can hide from a sky that Earth normally shields for us. That is a strange reversal. On Earth, we look up at the sky for weather. On Mars, the sky is part of the hazard, not because it is full of lightning or rain, but because it is too thin to defend the surface properly. That is another reason Mars is harder than it looks in animation. This does not mean astronauts cannot go. It means a Mars mission has to treat radiation as a central design problem from the beginning, not as an afterthought. Spacecraft layout, mission duration, propulsion choices, surface habitats, operational rules, medical monitoring, and emergency plans all connect to it. A simple story says, build a bigger rocket. The real story says, build an entire survival system that crosses deep space. And radiation is only the first invisible part of that system. Even if we shield the crew well enough, monitor the sun carefully, choose the mission timing wisely, and keep the dose within accepted limits, the human body is still making the journey in an environment it was never built for. The spacecraft may protect astronauts from some of the particles outside, but it cannot turn deep space into Earth. Inside the vehicle, gravity is missing. Muscles begin to change. Bones begin to respond. Fluids shift. Balance adapts to weightlessness. The body, which evolved under one constant downward pull, is suddenly asked to live for months without it, then land on another world and perform difficult work under a different gravity altogether. So the radiation wall is not the only wall between Earth and Mars. It is the first invisible one. The next is inside the astronauts themselves. Radiation is the invisible wall outside the spacecraft, but even if a crew could pass through it, another problem would be waiting inside their own bodies. A human being is not just a mind sitting inside a vehicle. A body is also a gravity machine. Every bone, muscle, blood vessel, and balance system has been shaped by one constant fact. Earth pulls downward. It pulls when we stand, when blood moves through the body, and when the inner ear tells the brain which way is up. Gravity is so ordinary that we almost never feel it as an environment. It feels like the background of reality. Space removes that background. Inside a spacecraft on the way to Mars, the crew would not simply be sitting in a metal room for months. They would be living in microgravity, where the body no longer has to support its own weight. At first, that sounds almost comfortable. Objects float. Movement becomes gentle. A person can push from one wall and drift across a cabin with almost no effort. But the body does not interpret that as comfort. It interprets it as disuse. On Earth, bones remain strong partly because they are loaded every day. The hips, spine, legs, and feet constantly carry weight. Muscles work even when we are doing nothing dramatic. Standing still is not truly doing nothing. The body is balancing, correcting, pushing, resisting, and absorbing force. Gravity keeps the system busy. In microgravity, much of that work disappears. The bones that normally carry load begin to lose mineral density. Muscles that no longer have to fight body weight begin to weaken. The heart and blood vessels adjust to a world where fluid is not pulled down into the legs in the same way. Even the eyes and the pressure around the brain can be affected in some astronauts during long missions. None of this means astronauts are fragile. It means they are human. The International Space Station has taught us a lot about living off Earth, but it is still close to home. It can receive cargo, crews, and support in ways a Mars mission cannot copy. A Mars crew would need the same discipline as station astronauts, and probably more. The problem is not only that their bodies change during the trip. The problem is what they have to do when the trip ends. A crew arriving at Mars would not step out into a hospital. They would arrive at a hostile planet, where the landing system has just completed one of the most difficult maneuvers in spaceflight. The astronauts might have to check the spacecraft, inspect suits, troubleshoot equipment, and begin the work of surviving on another world. They cannot arrive as patients. They have to arrive as workers. That requirement changes everything. If the body loses too much strength during the months-long journey, the danger is not just future health. It is mission performance. A weak crew may struggle to climb, carry, repair, suit up, respond to alarms, or recover from a rough landing. A dizzy crew may make mistakes at the exact moment when mistakes are least forgiving. Mars gives some gravity back, but not all of it. The surface gravity is only about 38% of Earth's. That sounds helpful after months of weightlessness, but it is also strange. Walking, lifting, falling, and moving inside a pressurized suit would all feel different. The crew would have to adapt more than once. First, microgravity on the way out. Then, partial gravity on Mars. Later, if the mission returns, microgravity again during the trip back, and full Earth gravity at the end. That sequence is one of the central reasons human Mars missions are not simply longer Apollo missions. The Moon missions were short. Mars demands months in transit, a long stay, or a carefully timed mission architecture, and a return journey that extends the stress. The body is not a machine that can be switched between gravity settings without consequence. Bone loss is one of the clearest examples. NASA has reported that without the right countermeasures, Weight-bearing bones can lose roughly 1 to 1.5% of mineral density per month in spaceflight. That may sound small until the months add up. Exercise, nutrition, and other countermeasures help, but help is not the same as erasing the problem. Muscle loss follows the same logic. If legs and back muscles do not have to support the body against gravity, they weaken. Astronauts fight this with resistive exercise devices, cycling, treadmills with harnesses, and carefully planned routines. On a Mars spacecraft, exercise equipment cannot be an afterthought. It has mass, volume, power requirements, maintenance needs, and failure modes. Exercise systems failing on the way to Mars could become a mission risk. Every solution has a cost. More exercise hardware means more mass, more fuel, and more complexity. Less hardware means higher health risk. Mars turns medical problems into engineering problems, and engineering problems back into medical ones. Fluid shifts are another example. On Earth, gravity pulls fluids downward. In microgravity, fluids shift toward the upper body and head. Faces can look puffy. Legs can become thinner. The body adjusts its fluid balance. Over time, these shifts may contribute to vision-related issues known as spaceflight-associated neuroocular syndrome, or SANS, which NASA treats as an important concern for long-duration missions. Vision matters on Mars. It sounds obvious, but it has to be said. Astronauts must read displays, inspect equipment, navigate terrain, operate tools, recognize hazards, and respond to small changes in their environment. Even mild vision changes can matter when the nearest emergency room is a planet away. Balance adds another layer. In microgravity, the inner ear receives signals it was not built to interpret. After adapting to floating, the crew must land on a planet and quickly become functional in partial gravity. That moment matters because landing is not the end of danger. It is the start of surface operations. Imagine the crew after months of travel. They have lived in a confined vehicle, exercised every day, managed radiation protocols, rationed supplies, and monitored each other medically. Their bodies have changed despite all countermeasures. Then the spacecraft enters Mars' atmosphere, shakes under heat and force, descends through dust and thin air, fires engines near the surface, and finally lands. The first minutes after landing may be full of checklists: pressure, power, communication, life support, vehicle stability, possible damage, and terrain assessment. A body weakened by the journey makes every one of those tasks harder. This is why the phrase human spaceflight is misleadingly clean. The spacecraft does not fly alone. It carries biology. That biology sleeps, adapts, heals, weakens, and sometimes fails in ways that do not appear in a rocket diagram. Engineers can calculate thrust, mass, fuel, and trajectory with extraordinary precision. A human crew brings variables that are harder to model: fatigue, bone loss, immune changes, injury, and the slow psychological effect of distance. Mars becomes less like a destination and more like a test of whether a small group of bodies can remain useful inside a hostile chain of environments. The spacecraft, deep space, Mars orbit, the landing sequence, the surface habitat, the suit, and the return vehicle all become separate environments. Each one asks the body to adjust, and each adjustment has limits. For now, the realistic path depends heavily on countermeasures: exercise, nutrition, medical monitoring, careful scheduling, and mission design that reduces unnecessary risk. Even then, uncertainty remains. The longest human missions so far have taught us a lot, but Mars is still a different challenge. A Mars crew would be exposed to microgravity, deep space radiation, confinement, communication delay, and mission stress at the same time. These hazards do not politely stay in separate boxes. Radiation can interact with health. Sleep loss can affect judgment. Isolation can affect teamwork. Reduced fitness can affect emergency response. A small injury can become larger when recovery options are limited. The body problem is not one problem. Like Mars itself, it is a chain. And the most dangerous chain links are often the ones people barely notice in the public story. Rockets are spectacular, so they dominate the imagination. Microgravity damage is quiet. Bone loss does not make a dramatic image. Fluid shifts do not explode. Muscle atrophy does not trend like a rocket landing. But on a crewed Mars mission, quiet problems can become mission-ending problems. The astronauts must not only survive the journey, they must arrive strong enough to land, work, repair, explore, and eventually leave. This is the key difference between sending humans and sending robots. A rover does not lose bone density. A rover does not become dizzy when gravity changes. If a rover breaks, the mission may be tragic, but no one has to keep it alive. A human crew is different. The spacecraft must become a moving ecosystem, a hospital, a gym, a workshop, a shelter, and a psychological container. Every system has to support the body, because the body is the mission. That is why Mars remains out of reach in a practical sense, even though we know the route. We can calculate trajectories, we can launch machines, we can land robots, but people bring Earth with them in fragile form. Blood evolved under Earth gravity. Bones evolved under Earth gravity. The brain expects Earth signals. The immune system, muscles, eyes and heart all come from a planet where down is always down. Mars asks those systems to endure something no generation of humans has ever endured completely. Months without weight, a landing on another planet, life under partial gravity, a return across deep space, and then full Earth gravity again. No part of that is impossible by itself, but every part must be understood well enough that the crew can remain capable when capability matters most. And capability matters immediately at Mars, because the next obstacle is not inside the body anymore. It is outside the window. Even if the astronauts arrive healthy, alert, and strong enough to work, the planet still has to let them down safely. Mars has already destroyed spacecraft that were far simpler and far lighter than anything humans would need. Its atmosphere is thick enough to create fire and turbulence, but too thin to make landing easy. It gives engineers the worst of both worlds: enough air to be dangerous, not enough air to be forgiving. After months of protecting the crew from the damage of weightlessness, the mission would enter the few minutes where physics gives almost no room for error. The body has to be ready. The spacecraft has to be ready. And Mars, as every mission planner knows, does not forgive a landing that is only almost successful. And even if the crew arrives strong enough to work, Mars still keeps its most unforgiving test for the final minutes. The journey can last for months. The astronauts can survive radiation, weightlessness, isolation, and the long silence between worlds. The spacecraft can cross millions of miles and arrive exactly where navigation predicted. Every system can perform well for most of the mission. Then, Mars has to be landed on. That sentence sounds simple only because every successful landing makes the process look inevitable afterward. A rover appears on the surface. A first image comes back. Engineers cheer. The world sees a machine sitting safely on red ground, and the danger becomes part of the celebration instead of the event itself. But landing on Mars is not a gentle arrival. It is a controlled emergency. A spacecraft approaches the planet at interplanetary speed. It has to enter the atmosphere, survive heating, slow down, navigate toward the right region, avoid dangerous terrain, deploy the right systems in the right order, and touch the surface softly enough that the mission does not end in wreckage. Mars gives almost no room for improvisation. The atmosphere is the first problem, because Mars has just enough of one to make landing violent, but not enough to make landing easy. On the Moon, there is essentially no air. A vehicle can descend under rocket power without worrying about aerodynamic heating. On Earth, the atmosphere is thick enough that capsules can use it heavily to slow down, even though re-entry is still dangerous. Mars sits in the cruel middle. Its atmosphere is thick enough that a spacecraft cannot ignore it. Arrive too fast, and the vehicle heats fiercely as it punches into the thin carbon dioxide air. A heat shield is not optional. The lander has to survive a fiery entry, with its outer protection absorbing energy that would otherwise destroy the vehicle. Yet the same atmosphere is too thin to slow a heavy spacecraft all the way down with parachutes alone. That is the trap. Too much air to treat Mars like the Moon. Too little air to treat it like Earth. For robotic missions, engineers have solved this problem with a chain of carefully timed systems. A heat shield takes the first hit. A parachute opens at supersonic speed. Radar measures altitude and velocity. Rockets fire. For Curiosity and Perseverance, the famous Sky Crane lowered the rover on cables while a rocket-powered descent stage hovered above the surface, then flew away to crash at a safe distance. That sequence sounds almost ridiculous until you remember why it exists. Mars does not allow one simple solution. A parachute alone is not enough. Rockets alone would require too much fuel if they had to do all the work from the beginning. A heat shield alone cannot land anything. So the descent becomes choreography. Each system does a part of the job and then hands the mission to the next system at the right second. If one part fails, the next may never get a chance. For a robot, that is terrifying enough. For humans, it becomes a different category. NASA studies often describe the human-class Mars landing problem as a jump to payloads far heavier than what has been landed before, with landed masses over 20 metric tons being discussed for some mission elements. That is not a small improvement over past rovers. It is a leap. Mars has never proven that it can forgive such a leap. The atmosphere that struggled to slow one-ton class robotic spacecraft becomes even less cooperative when the payload becomes many times heavier. A larger lander needs a larger heat shield. It carries more kinetic energy. It may need powerful supersonic retropropulsion, meaning rockets firing while the vehicle is still moving fast through the atmosphere. It may need new aeroshell designs, inflatable decelerators, advanced guidance, and landing systems that have never been used at that scale on Mars. Every kilogram matters, but safety demands mass. That is the contradiction built into human landing. Astronauts need protection, redundancy, supplies, and volume. Mars punishes all of those things because heavier vehicles are harder to slow and harder to land. Make the lander lighter, and safety can shrink. Make it safer, and mass grows. The engineering problem becomes a negotiation with a planet that does not negotiate back. A robotic mission can fail and become a tragedy for science, money, and years of work. A human landing failure becomes a loss of life, watched by the entire planet with a communication delay that prevents anyone from helping in real time. Mission Control could understand what is happening and still be unable to change the outcome fast enough. During entry, descent, and landing, the crew and spacecraft are committed. The atmosphere decides quickly. Mars does not offer a runway. There are no repair teams waiting on the surface, no rescue helicopters, no second lander that can quickly move across the planet. If the vehicle touches down too hard, tips over, lands on rocks, damages an engine, blocks an airlock, ruptures a tank, or misses the prepared zone by too far, the entire mission can change in one violent moment. A Mars landing is not only about reaching the surface, It is about reaching the right surface in the right condition. Human missions will probably not land randomly wherever the safest open plain happens to be. They need access to resources, sunlight, terrain that can support surface operations, and possibly pre-landed cargo. If oxygen production equipment, return fuel systems, habitats, and supplies are sent ahead, the crew must land close enough to use them. A landing that is technically successful but too far from the mission infrastructure may still be a disaster. Precision becomes survival. Robotic missions already care about terrain. Perseverance used terrain relative navigation to help avoid hazards and land in Jezero Crater, a scientifically valuable place with ancient river delta features. For humans, that kind of intelligence becomes even more important. The Lambda may need to avoid cliffs, slopes, boulder fields, soft dust, and areas that could damage engines or landing legs. It may need to land near cargo without blasting it with debris. Rocket exhaust can throw dust and rocks at high speed. Visibility may drop. Sensors may have to work through dust and vibration while the vehicle is running out of altitude. The final seconds could be the most violent quiet in the mission. Inside the crew cabin, astronauts may not see Mars as a peaceful red landscape. They may see numbers, warnings, vibrations, and a vehicle fighting to convert deadly speed into stillness. The surface that looked motionless from orbit becomes a problem of meters per second, fuel margins, engine thrust, landing gear loads, and the difference between a safe touchdown and a permanent accident. Nothing about that is solved just because rockets exist. Leaving Earth is enormous, but Mars landing is a different kind of hard. Launch happens from Earth, with infrastructure, weather monitoring, abort systems, and recovery zones. Mars landing happens once per mission, far away, with no ground crew, no direct control, and no chance to pause. The vehicle cannot hover forever while engineers think. Fuel is limited. Altitude is vanishing. The atmosphere is changing around the spacecraft second by second. That is why Mars is not stopped by one missing invention. It is stopped by integration. The heat shield has to work with the decelerator. The guidance system has to work with propulsion. The engines have to work in a thin atmosphere above uncertain ground. The landing legs have to handle uneven terrain. The crew systems have to keep people alive through it all. The target site has to be useful after landing, not merely survivable during touchdown. A mostly successful landing is not enough. A rover can survive with some damage and still perhaps do science. A human mission has less tolerance for failure. A damaged solar array, clogged radiator, cracked pressure seal, broken rover, blocked hatch, or fuel system leak could become life-threatening. The landing is not the end of risk. It is the beginning of surface dependency. The astronauts do not step onto Mars as explorers who have finished the hard part. They step out as survivors of the first impossible sequence, surrounded by the next one. This is why Mars has been visited by robots first. Robots are lighter, simpler, and more willing to die. They do not need oxygen. They do not suffer panic. They do not need a medical bay, sleeping quarters, exercise equipment, food storage, privacy, or a way home. If a robot lands too far from ideal terrain, the mission adapts. If it breaks, the loss is painful but not human. Mars is not hostile in the emotional sense. It simply has gravity, atmosphere, terrain, dust, and distance. Human beings are the ones bringing fragility into that environment. We are the ones who need pressure, temperature, oxygen, soft landing loads, working electronics, and a habitat that is not cracked on arrival. From orbit, Mars can look almost inviting. Valleys, volcanoes, canyons, plains, polar caps. A world with geography, a place you can imagine walking across. The descent strips that romance away. Before anyone can walk, A heavy machine has to survive a plunge through thin air, slow itself from interplanetary speed, choose a patch of ground, avoid hazards, land upright, remain sealed, and be ready to become the crew's only home on an alien planet. The fact that we have landed robots does not make this easy. It proves that Mars landing is possible. It does not prove that landing humans is just the same problem scaled up. Scaling up is exactly where the danger lives. So before humans can reach the surface, landing has to become boring in a way it has never been. Not boring to watch, but boring to trust. The system has to be so well understood, so tested, so redundant, and so precise that placing a human-class vehicle on Mars no longer feels like balancing a civilization on the edge of a coin. We are not there yet. That does not mean we will never get there. It means the red planet is still asking for proof. And even after that proof is finally given, even after the heat shield survives, the engines fire correctly, the vehicle stands upright, and the crew hears the words that they are safely on Mars, the real mission does not end. The hatch is still closed. Outside is not another version of Earth. Outside is a frozen, low-pressure desert under a sky that cannot be breathed, with radiation still falling from above and dust waiting for every seal, joint, suit, and machine. Landing gets humans to Mars. Surviving Mars is the next problem. If the crew survives the landing, the mission does not become easier. It becomes more honest. From orbit, Mars can look almost familiar. There are polar caps, clouds, canyons, volcanoes, river valleys, dust storms, seasons, and a day only a little longer than Earth's. In photographs, the surface can resemble a desert on our own planet, red and quiet under a pale sky. That resemblance is powerful because the human mind searches for home everywhere it looks. But Mars is not a backup Earth. It is not a cold version of Arizona waiting for tents and solar panels. It is not a place where astronauts step out, take a breath, and begin building a new world with ordinary tools. The moment the lander opens, every living cell in the crew depends on machines. The air outside is not air in the human sense. Mars has an atmosphere, but it is thin and mostly carbon dioxide. There is no usable oxygen for breathing. The pressure at the surface is far too low for an unprotected human body. Water behaves differently under that pressure. Heat escapes easily. The sky can be bright, but the world below it remains hostile. That is the first shock after landing. The planet is there, under their boots. The horizon is real. The dust is real. And still, almost nothing about the environment is willing to keep a human alive. A spacesuit on Mars is not clothing. It is a small spacecraft shaped around a body. It has to provide pressure, oxygen, temperature control, carbon dioxide removal, dust protection, mobility, and communication. A tear is not an inconvenience. A failed seal is not a delay. The suit is the boundary between a person and a planet that cannot support them. The habitat is the same idea made larger. It is not a house. It is a pressure vessel with rooms inside. Every wall has to separate warm, breathable air from a freezing low-pressure world outside. Every hatch has to work. Every airlock cycle matters. Every filter, pump, valve, cable, sensor, battery, and backup system becomes part of the crew's survival. On Earth, a building protects you from weather. On Mars, a habitat protects you from the planet itself. That changes the meaning of shelter. A Mars base cannot simply be comfortable. It has to be closed, repairable, redundant, and resistant to dust, cold, radiation, and human error. It has to hold pressure every hour of every day. It has to survive when the crew is tired, when equipment is aging, and when the next supply ship is not coming tomorrow. The ground outside the habitat may look still, But stillness does not mean safety. Mars is cold in a way that reaches into engineering. Average temperatures are far below freezing. Metal contracts, seals stiffen. Batteries lose performance. Lubricants behave differently. Electronics need thermal management. Water lines cannot be allowed to freeze. A machine that works in a laboratory on Earth has to become a machine that works after months of dust, cold, vibration, and delayed repairs. Cold is not only uncomfortable. Cold is a design problem. Then there is the air, thin enough to make flying difficult, but thick enough to move dust around the planet. That combination is one of Mars's cruel tricks. The atmosphere does not give humans enough pressure or oxygen to live. It does not slow heavy spacecraft easily during landing. It does not block radiation the way Earth's atmosphere does. Yet it can still drive winds, lift fine particles, and wrap machinery in dust. Martian dust is not just dirt. It is a mission problem. The particles are extremely fine. They can cling to surfaces because of electrostatic effects. They can coat solar panels, reduce power, get into joints, scratch seals, cloud sensors, contaminate equipment, and follow astronauts through airlocks. If enough dust enters the habitat, it becomes a health concern as well as an engineering one. Lungs evolved for Earth, not for breathing traces of alien regolith inside a closed environment. Science fiction often imagines Martian winds as if they could throw astronauts across the surface. In reality, because the atmosphere is so thin, the force of the wind is much weaker than a similar speed wind on Earth. But that does not make dust harmless. It can settle slowly, invade mechanisms, reduce sunlight, and become a constant maintenance burden. Dust storms add another layer. Some storms are local, some become regional. Rare global storms can darken the sky across much of the planet. For solar-powered systems, that matters immediately. Less sunlight means less power. Less power means less margin for heating, communication, mobility, oxygen production, science operations, and emergency response. A crew living on Mars would need to plan for days or weeks when the sun is present but weakened behind suspended dust. Mars looks still because we often see it in single images. In reality, the planet has weather. Not friendly weather. Thin, dusty, cold weather. Weather that can change power budgets and visibility, cover equipment, and force astronauts to wait inside while a mission clock keeps moving. Above all of this is radiation. Mars does not have Earth's thick atmosphere or global magnetic field to provide the same level of protection on the surface. The crew has already dealt with radiation during the trip through deep space, but landing does not make the problem vanish. The surface is safer than open space in some directions because the planet itself blocks half the sky. But the atmosphere is not enough to make Mars feel like Earth. Cosmic rays still matter. Solar particle events still matter. Ultraviolet radiation still matters because Mars lacks the kind of ozone shield that protects Earth. A habitat cannot be only airtight. It may need shielding. Some designs imagine using regolith, water, ice, or special materials to reduce exposure. The crew may need storm shelters for solar events. On Earth, the sky protects us so quietly that we forget the service it provides. On Mars, protection has to be built. That is the difference between exploring an environment and surviving one. The surface also contains chemical problems. Martian soil is not garden soil. It is regolith shaped by impacts, radiation, dust, and ancient geology. Certain reactive salts, including perchlorates detected by Mars missions, complicate any simple dream of scooping red dirt into a greenhouse and growing food. They must be understood, processed, removed, or managed. Again, Mars refuses the easy version. It may contain resources. It does not hand them over cleanly. Every simple word becomes a system. Air, water, food, heat, power, waste. On Earth, these words disappear into the background because the planet does much of the work. The atmosphere holds pressure. Rivers and rain move water. Soil hosts biology. The magnetic field and ozone layer help soften radiation. If something breaks in one city, help can come from another. Mars offers none of that background generosity. A crew cannot depend on open air, open water, open soil, or open rescue. They have to bring a pocket of Earth with them and keep it alive. That phrase may be the truest description of a Mars base. Not humans living on Mars, a piece of Earth being maintained on Mars. Inside the habitat, the crew would breathe an engineered atmosphere. They would drink recycled water. They would sleep in a pressurized shell. Their carbon dioxide would be scrubbed. Their oxygen would be monitored. Their suits would be checked before every excursion. Survival becomes routine. A mission can survive one emergency if the crew is trained and the system has backup. The harder challenge is not one dramatic failure. It is the accumulation of ordinary stress. Dust on seals, minor leaks, clogged filters, worn joints, tired people, delayed messages, equipment behaving slightly worse than expected, a storm that reduces power at the wrong time. Mars is not only dangerous when something spectacular happens, it is dangerous because the margin for ordinary imperfection is small. That is what makes the surface phase so different from planting a flag on the moon. Apollo astronauts stayed for days. A Mars mission would likely require a much longer stay because orbital mechanics decide when the return path becomes practical. The crew cannot simply land, take samples, and leave whenever they choose. Once they are there, they may be committed to living with Mars for months. That long stay changes everything. A short mission can carry more from home. A long mission needs systems that keep working. A short mission can accept more discomfort. A long mission has to manage health, morale, repairs, science, and risk over time. A short mission can treat the habitat as a temporary shelter. A long mission turns it into the center of a small world. The landscape outside may be magnificent. The first human to stand on Mars will see something no one has ever seen with living eyes. The horizon of another planet under another sky. The ground will hold ancient stories of water, volcanoes, impacts, and climate change. Somewhere in those rocks may be clues about whether life ever began beyond Earth. But the beauty does not make the place friendly. A person could stand beside a valley carved by ancient water and die because there is no air to breathe. They could look at a sunset colored by dust and die because the suit lost pressure. Mars is full of reminders that similarity is not safety. This is one of the reasons robots have gone first. A rover can freeze, break, reboot, wait, and continue slowly. It does not need to breathe. It does not suffer bone loss. It does not panic in isolation. If it dies, the loss is painful and expensive, but no family receives a body from another planet. The surface of Mars is therefore not just a destination after the hard landing. It is a test of whether humans can create a closed, repairable, semi-independent life support island in a world that offers almost nothing freely. That is why Mars is not a backup Earth. A backup Earth would be a place where the environment helps. Mars is a place where the environment resists. It has useful materials, but they are locked behind extraction. It has atmosphere, but not breathable air. It has sunlight, but weakened and dust-filtered. It has water, but frozen, hidden, or chemically complicated. It has ground, but not soil, in the human agricultural sense. It has a sky, but not a shield. That is the real surface mission, not walking on Mars, but staying alive on Mars. And staying alive leads directly to the next problem, because carrying every breath, every liter of water, and every kilogram of return fuel from Earth makes the mission brutally heavy. To live on Mars for long, humans cannot treat the planet as only a place to stand. They have to learn how to use what is already there. Survival begins with resisting Mars. The next step is asking whether Mars can be made to help. And once survival depends on machines, Mars becomes a different kind of problem. You cannot bring an entire planet with you. A crew on Mars would need air every minute, water every day, power through dust and cold, spare parts for failures, and fuel for the return. On Earth, those needs hide in the background because the planet provides them almost for free. The air is already mixed. Water moves through clouds, rivers, oceans, and ice. Food grows under a thick atmosphere. If a machine breaks, there are roads, factories, hospitals, and people nearby. Mars offers materials, but not comfort. Its atmosphere is there, but it is thin and mostly carbon dioxide. Water exists, but not as a stream beside the habitat. Oxygen exists inside carbon dioxide, minerals, and ice, but not as breathable air. The ground may hold useful resources, but it also holds dust, salts, rocks, local surprises, and the simple difficulty of mining on another planet while wearing a pressure suit. That is why living off the land is not a romantic bonus for Mars. It may be the difference between a short visit and a real mission. In spaceflight, every kilogram matters. Anything launched from Earth must climb out of Earth's gravity, survive the trip, reach Mars, and often land through the Martian atmosphere. Food, water, oxygen tanks, machinery, shielding tools, and spare parts all compete for mass. Add more supplies, and the spacecraft grows. A larger spacecraft needs more propellant. More propellant needs larger tanks. The mission expands around every extra kilogram. So the dream cannot be to carry a small Earth across space. At some point, the mission has to use Mars itself. The technical name is In Situ Resource Utilization, or ISRU. The idea is simple enough. Use what is already there. On Mars, that could mean extracting oxygen from the carbon dioxide atmosphere, mining buried water ice, making propellant, or using local material as shielding and construction mass. In the easy version, it sounds obvious. Use the carbon dioxide, melt the ice, build with the dirt. The real version is harder because a resource is not useful just because it exists. It has to be found, extracted, purified, stored, protected, and used by systems that keep working without a repair shop from Earth. Every resource has to pass through a machine before it becomes survival. That is why one of the most important experiments on Mars was a small oxygen-making device on Perseverance, MOXIE. The Mars Oxygen In Situ Resource Utilization Experiment was not a factory. It did not make enough oxygen to support a crew, but it proved something that matters deeply for the future. Oxygen can be produced on Mars from the Martian atmosphere. Mars air is mostly carbon dioxide, molecules made from carbon and oxygen. MOXIE pulled in that thin air, processed it, and split oxygen away from carbon dioxide. Across its tests, it produced oxygen again and again, showing that the basic process could work in the real Martian environment. That is a huge step. It is also not the same as solving Mars. A small demonstration is not a full life support and propellant system. A crew would need oxygen for breathing, but oxygen is also a major part of rocket propellant. Rockets do not only need fuel, they need oxidizer. If astronauts are going to leave Mars, producing oxygen locally could reduce the amount that must be launched from Earth and landed before them. That is why MOXIE matters more than its size suggests. It made the first link in a much larger chain look possible. But possible is not enough for a human mission. A full-scale system would have to run for long periods, probably before the crew even arrives. It would have to make oxygen reliably, compress it, cool it if needed, store it, monitor it, and protect itself from dust, cold, leaks, wear, and power interruptions. It would need backups, because a single-point failure in an oxygen factory is not a small inconvenience when the return ticket depends on it. That is the harsh rule of Mars ISRU. The machine has to work before it is celebrated. A future crew might not land until the return propellant has already been produced and verified. That sounds cautious, but it may be necessary. No responsible mission wants astronauts standing on Mars while a broken factory decides whether they can go home. If an oxygen plant fails before launch from Earth, the mission can be delayed. If it fails after the crew lands, the problem becomes personal. In that sense, the return mission may begin long before the astronauts leave Earth. It begins with machines on Mars quietly making and storing what the humans will need later. Oxygen is only one part of the problem. Water may be even more important. Water is life support, chemistry, hygiene, cooling, radiation shielding, and possibly fuel production. Split water into hydrogen and oxygen. Combine hydrogen with carbon dioxide. And mission designers can imagine producing methane and oxygen propellant. Use water as mass around a habitat, and it can help reduce radiation exposure. Give it to a crew, recycle it, clean it, and the habitat becomes less dependent on shipments from Earth. But Mars does not give water away easily at the places humans would most want to land. The polar caps contain ice, but polar landing sites create problems with temperature, sunlight, terrain, and operations. Mid-latitude buried ice is more attractive for future crews because it may be closer to practical landing and working zones. Orbital data has revealed important signs of ice beneath the surface in some regions, but a map is not a water supply. A human mission needs more than proof that ice exists somewhere. It needs ice close enough to reach, shallow enough to extract, clean enough to matter, and located where landing, power, communications, science, and survival all still make sense. Those needs may not overlap perfectly, so Mars forces mission planners to trade one advantage against another. Suppose a mission lands near accessible buried ice. The crew still has to get it. That means drilling, heating, hauling, filtering, and storing material that may be mixed with dust and salts. Pipes cannot freeze. Pumps cannot jam. Storage tanks cannot leak. The mine cannot become a single fragile machine that decides whether the base lives. On Earth, mining is difficult even with roads, workers, heavy equipment, and replacement parts. On Mars, the mine might have to begin with a few astronauts and a machine that cannot call for a mechanic. This is where the fantasy of just use the ice becomes too simple. The ice is not a lake beside the habitat. It is a resource embedded in a hostile environment, and every step between buried ice and usable water becomes part of the mission architecture. Find it, reach it, extract it, purify it, store it, recycle it, then use it without wasting it. Food adds another layer. A Mars greenhouse would not be an ordinary garden, but a pressure vessel with water, air, nutrients, lighting, temperature control, and protection from dust and radiation. Early crews will bring most of their food, but even a small amount of fresh growth could help nutrition and morale. Martian regolith is not Earth soil, so every crop would be an engineered system before it became dinner. This is why living off the land is not a single technology. It is an ecosystem of machines. An oxygen plant by itself does not make a Mars base. A water drill by itself does not make a Mars base. A greenhouse by itself does not make a Mars base. Each one depends on power, maintenance, storage, software, sensors, spare parts, and humans capable of repairing it while tired, isolated, and far from help. The phrase local resources can sound like freedom. In reality, it creates a new kind of dependence. Instead of depending only on cargo launched from Earth, the crew depends on machines that convert Mars into something usable. If those machines work, the mission becomes more possible. If they fail, the planet around the crew remains full of resources they cannot reach. Mars can be rich and useless at the same time. A resource does not save you until your system can use it. Power sits beneath all of this. Oxygen production, water extraction, heating, drilling, communications, recycling, lighting, rover charging, science operations, and medical systems all need energy. Mars receives less sunlight than Earth, and dust can reduce solar power. Nuclear power could offer steadier energy through night, winter, and storms. But it brings its own challenges in launch, landing, deployment, cooling, and shielding. No energy source is free of trade-offs. A Mars base is not just a habitat. It is a power plant, an air plant, a water plant, a recycling plant, a workshop, a medical station, a communications node, a laboratory, and eventually a launch site. That is why humans still have not reached Mars. Not because one impossible mystery stands in the way, but because each requirement multiplies the next. Bring no local resource systems, and the mass from Earth becomes brutal. Depend on local resources, and the pre-deployed machines must work with near-perfect reliability. Use solar power, and dust and season matter. Mine ice, and geology join survival. Mars is not stopping humans with one locked door. It is asking for a whole keyring. Professional exploration lives in the gap between demonstration and dependable infrastructure. If humans ever do reach Mars, the first footprint will not be the real victory by itself. The greater victory will be everything already working behind it. Tanks filled before arrival, habitats checked before landing, power systems running, air systems tested, water plans verified, spare parts available, rovers charged, and ascent vehicles waiting. That is the difference between planting a flag and surviving. A flag only needs a moment. A human mission needs continuity. Every local resource system is an attempt to turn Mars from a place that kills into a place that can help. For now, Mars mostly remains material without mercy. Nothing there is automatically useful. Everything has to be earned. That leads naturally into the next part of the problem. Even if the crew has air, water, power, and a habitat, they will not have real-time help from mission control or cargo ships arriving on a schedule. Mars will force them to become more independent than any crew in history. A machine can make oxygen, a drill can find ice, a habitat can hold pressure. But when something breaks, when someone gets sick, or when a warning light appears at 2 a.m. on a world no human has ever survived on before, the crew will face another truth about Mars. There is no quick rescue, and there is no real-time help. Even if the crew can make oxygen, find water, store power, and keep the habitat alive, Mars still leaves them with a problem that feels almost psychological before it becomes technical. They are alone. Not alone because Earth has forgotten them. Mission Control would be watching every signal, every system, every medical reading the crew chooses to send back. Families would still record messages. Engineers would still work around the clock. But Mars does not allow real-time help. That changes the mission. On the International Space Station, Earth is close in every meaningful way. Astronauts orbit only a few hundred kilometers above the surface. They can speak with mission control almost instantly. If something breaks, ground teams can walk them through procedures step by step. Cargo ships can bring supplies. In a severe emergency, the crew has a way home. Mars removes that comfort. A message between Earth and Mars does not arrive instantly because light itself needs time to cross the gap. Depending on where the planets are in their orbits, a one-way signal can take minutes and at worst, close to 20 minutes. That means a simple question and answer can become a conversation stretched across nearly 40 minutes or more. A doctor cannot talk an astronaut through a crisis in real time. An engineer cannot watch a pressure drop and respond like someone standing in the next room. A commander on Mars cannot ask for permission before every dangerous decision, because permission may come too late to matter. This is one of the reasons Mars is not just farther than the Moon. It is operationally different. The Moon still allows near real-time communication. Mars turns communication into correspondence. That sounds small until something goes wrong. Imagine a warning light inside the habitat. Maybe the carbon dioxide removal system is behaving strangely. Maybe an airlock sensor gives conflicting readings. Maybe a rover loses traction several kilometers from base. Maybe a crew member develops pain, fever, blurred vision, an injury, or symptoms nobody expected. On Earth, teams would gather instantly. Specialists would join the Corps. Data would be reviewed while the crew waits. On the space station, that model works because Earth is close enough to remain part of the room. On Mars, the crew may have to become the room. They will need the training of astronauts, engineers, medics, mechanics, scientists, pilots, and emergency responders folded into one small group. They will not have the luxury of being passengers in a spacecraft guided from far away. The mission will demand autonomy, not as a nice feature, but as survival. Autonomy sounds empowering from the outside. Inside a crisis, it means wait. The crew must decide when a system is safe enough to keep running, when a repair is worth the risk, whether a medical problem can wait, and whether using a spare part today will create a worse problem months later. Every choice uses time, energy, equipment, and confidence. None of those are unlimited. The psychological burden of that independence may be as important as the engineering. A Mars crew would live in a small world with no natural escape. The habitat is shelter, workplace, bedroom, laboratory, kitchen, medical station, and storm bunker. Outside the walls is an environment that cannot support an unprotected human body. That kind of confinement is not simply boring. It changes people. Sleep can be disrupted. Workload can become heavy. Small conflicts can grow because there is nowhere else to go. Privacy is limited. The same few voices fill every day. Earth becomes a screen, a delay, and a memory. The crew sees home as a blue point in the sky, but they cannot touch it, return to it quickly, or call it in the ordinary way. Humans are social animals, but a Mars mission forces social life into an extreme container. A bad day on Earth can be softened by walking outside, seeing different people, changing rooms, driving somewhere, or letting time create distance. On Mars, distance does not create relief. Distance is the problem. The crew carries the same relationships into every room and every task. This is why selection and training matter so much. Technical skill alone is not enough. Mars needs people who can repair machines and repair trust. People who can be honest without becoming destructive, and independent without becoming reckless. Popular images of Mars focus on the first footprint, the flag, the red horizon, the suit against the dust. But most of the mission would be maintenance, exercise, cleaning filters, checking seals, logging data, testing water, inspecting dust contamination, and repeating tasks because repetition is what keeps life support from becoming a headline. A crew does not survive Mars by feeling inspired every morning. They survive by doing the unglamorous things correctly. That is also why communication delay affects more than emergencies. It changes ordinary work. A robot on Mars can receive commands, execute them slowly, and wait for the next instruction. A human crew cannot be managed like a rover, but neither can it be supported like a crew in low Earth orbit. Mission control will still plan, analyze, and advise. But daily life must include more local decision-making. The astronauts have to understand the mission well enough to improvise without breaking it. Too much control from Earth, and the delay becomes dangerous. Too much freedom without structure, and the crew may drift away from the safest procedures. A professional Mars mission would need new habits of trust between Earth and the crew. Mission control would not vanish, but it would become less like someone holding the steering wheel and more like a distant partner writing letters into the future. Then there is medicine. This may be one of the clearest ways to understand why Mars is different. On the space station, if a medical issue becomes severe enough, evacuation is at least physically possible. It may be difficult, dangerous, and disruptive, but Earth is nearby. A crew member can return in a spacecraft. On Mars, there is no quick evacuation. A broken bone, kidney stone, infection, allergic reaction, dental emergency, eye problem, radiation-related issue, or psychological crisis cannot be solved by bringing the person home tomorrow. Surgery, if ever required, would be unimaginably complicated. Diagnosis would be harder without a full hospital. Medication supplies would be limited. Equipment must be compact, reliable, and useful for many possible problems. The crew medical officer would be working in a habitat with limited room, limited imaging, limited sterile capability, and no immediate backup. Remote doctors on Earth could advise, but not in real time. By the time a question travels to Earth and an answer returns, the situation may have changed. Mars medicine must be designed for independence. That means training the crew before launch. It means building decision support tools. It means carrying diagnostic equipment that can survive the mission. It means choosing medicines carefully, because every item has mass, volume, shelf life, and storage requirements. A medicine cabinet for Mars is not just a cabinet. It is a set of bets about what might go wrong. Spare parts work the same way. Every machine on Mars is a machine that cannot be casually replaced. A broken pump, fan, valve, seal, filter, battery, sensor, circuit board, compressor, or rover component can become serious because resupply is not close. Engineers can design redundancy, but redundancy adds mass. They can carry spares, but spares also add mass. Some parts might be manufactured locally, but not everything can be printed from Martian dust. A crew on Mars will live inside a supply chain that is stretched across planets. That supply chain cannot be treated like delivery. Launch windows matter. Cargo may need to be sent ahead years before the crew arrives. Critical systems may have to operate automatically before anyone is there to repair them. Food, tools, replacement parts, science equipment, habitats, power systems, ascent hardware, and return infrastructure must all be coordinated across time. The result is that Mars becomes less like a trip and more like a temporary civilization. Small, fragile, and dependent on planning. This is the deeper reason no rescue matters. Rescue is not only about dramatic emergencies. Rescue is the comfort that someone else can step in when planning fails. On Mars, every failure has to be absorbed locally, or anticipated before launch, or avoided through design. The margin for surprise becomes smaller. That does not mean a Mars crew would be helpless. They would be among the most capable humans ever assembled, trained through simulations, analog environments, field tests, and emergency rehearsals. But training does not remove isolation. It only prepares people to function inside it. The crew must remain clear-minded under conditions that naturally push against clarity. They have to sleep, work, exercise, repair, explore, conserve supplies, manage risk, and keep living together while Earth is always present emotionally and absent physically. That combination is difficult to explain to anyone who has never been trapped far from help. Mars is not lonely because it is empty. Mars is lonely because home is visible in the mind and unreachable in practice. A mission can fail through a dramatic explosion, but it can also fail through fatigue, conflict, bad judgment, degraded morale, or a small maintenance issue that grows because everyone is tired. Long-duration exploration makes human performance part of the hardware. The brain becomes a mission system. Trust becomes a mission system. Sleep becomes a mission system. Team culture becomes a mission system. If any of them fail badly enough, the spacecraft and habitat can be perfect and still not be enough. That is why the answer to why humans have not reached Mars cannot be reduced to rockets. Rockets start the journey. They do not solve the years of independence that follow. A crew living on Mars must be able to act before Earth answers, heal before rescue exists, repair before replacement arrives, and stay human inside a place that offers no comfort for human life. And even if they manage all of that, even if the habitat works, the crew holds together, the medical system is enough, the communication delay becomes routine, and Mars becomes a temporary home instead of a trap, the mission is still not complete. Surviving on Mars is not the final step. The crew still has to leave. A human mission is not truly successful when boots touch the red dust. It is successful only when those same people lift off from Mars, meet the spacecraft that can bring them home, cross interplanetary space again, and return through Earth's atmosphere alive. That return ticket is the next obstacle, and it may be the most unforgiving one of all. Even if every problem before this has been solved, the mission is still not finished. That is the detail Mars keeps forcing back into the story. A crew can survive the launch from Earth. They can cross interplanetary space. They can endure radiation, weightlessness, isolation, and months of distance. They can land safely on Mars, step onto the surface, live inside a habitat, make repairs, manage dust, collect samples, operate rovers, and look out through a small window at a landscape no human being has ever stood inside. But that is not the end of a human Mars mission. It is the middle. For a robotic rover, reaching Mars is often the victory. If the rover lands, wakes up, sends back data and begins moving, the mission has already done something extraordinary. No one expects it to come home. Curiosity is still on Mars. Perseverance is still on Mars. Spirit and opportunity remained on Mars. Machines can be sent one way. Humans cannot be treated like that. A crewed Mars mission is not Earth to Mars. It is Earth to Mars to Earth. That second half changes the entire architecture. Somewhere in the plan, there must be a way to leave Mars again. A rocket has to wait there, or be assembled there, or use fuel made there, or arrive before the crew. It has to survive the cold, the dust, the long surface stay, and the months or years of exposure before it is needed. Then, at the most important moment, it has to ignite. Not on a launch pad surrounded by thousands of engineers, not beside a tower on Earth, on another planet. That is why the return ticket may be one of the most unforgiving parts of the whole mission. Mars has less gravity than Earth, so launching from its surface is easier, in one sense. A rocket does not have to fight the same deep gravity well that makes Earth launch so brutal. There is also no thick lower atmosphere to punch through. But easier does not mean easy. Mars still has gravity. It still has an atmosphere, thin enough to complicate flight, but not thick enough to behave like Earth. It has dust, low temperatures, limited infrastructure, and no rescue vehicle sitting on the next pad. A Mars ascent vehicle has to do something no human-rated rocket has ever done. It has to lift people from the surface of another planet and put them into Mars orbit. Now imagine scaling the idea from sealed sample tubes to living astronauts. The difference is not just mass, it is reliability. A sample container does not panic. It does not breathe. It does not need a pressurized cabin, seats, controls, displays, life support, abort logic, thermal protection for people, medical safety, or a way to survive if the rendezvous takes longer than expected. A human ascent vehicle is not just a rocket. It is a temporary spacecraft built for one of the most critical climbs in human history. Mars orbit is not home. It is only the meeting place. The astronauts would have to rendezvous with another vehicle, perhaps an orbiting habitat or Earth return spacecraft. That rendezvous has to happen with precision. A mistake around Earth can sometimes be supported by tracking stations, fast communication, and rescue possibilities that still belong to the Earth system. Around Mars, the crew is alone, in a much larger silence. If the ascent vehicle misses its target orbit, the problem can become fatal. If the docking system fails, the problem can become fatal. If the return vehicle is not healthy when they arrive, the problem can become fatal. The mission may have survived the landing and the surface stay, only to become trapped above the planet it finally reached. That is the nature of Mars. Each success simply delivers the crew to the next place where failure is unacceptable. Before the launch from Mars can even happen, another question has to be answered. Where does the propellant come from? One approach is to bring it all from Earth. That sounds simple until mass starts multiplying backward through the mission. Every kilogram needed for ascent has to be delivered to Mars. To deliver it to Mars, more mass has to be launched from Earth. To land it on Mars, the descent system becomes larger. To protect and control the descent system, the spacecraft becomes larger again. Spaceflight punishes mass with a kind of mathematical cruelty. The farther the cargo has to go, the heavier its support becomes. That is why mission planners are interested in making some resources on Mars itself. If oxygen or propellant ingredients can be produced from Martian resources, the return architecture may become more practical. Mars has a carbon dioxide atmosphere. There is water ice in some regions. In theory, those resources can support oxygen production and fuel production, but in theory is not the same as ready for a crew. MOXIE, carried by Perseverance, was a brilliant demonstration because it proved that oxygen can be extracted from the carbon dioxide atmosphere of Mars on a small scale. That matters. It is a real step away from pure imagination. Yet a demonstration that makes grams of oxygen is not the same as an industrial system that fills tanks for a human mission. A full-scale system would have to run for long periods, handle dust, survive temperature swings, store oxygen safely, and report its health long before the crew commits to landing. The timing matters. If the return propellant is made on Mars, many mission plans would want it ready before the astronauts arrive. No crew should land on the promise that the fuel system will probably work later. The safer logic is brutal. Prove the return system is available before people descend to the surface. Otherwise, Mars becomes a trap built out of optimism. This is where the return ticket reaches backward and changes the beginning of the mission. The ascent vehicle may need to be pre-positioned. The fuel plant may need to operate ahead of the crew. Power systems may need to be landed first. Storage tanks may need to survive months of waiting. The crew might not even leave Earth until robotic systems on Mars have confirmed that the path home is real. That means humans do not simply arrive and begin exploring. Their future has to be waiting for them. Launching from Mars also means launching after months of living there. The crew will not be fresh in the way astronauts are on launch day at Kennedy Space Center. They may be physically adapted to partial gravity after a long journey and surface stay. They may be tired. Equipment may be worn. Dust may have entered seals, joints, tools, and suit systems, despite every precaution. A storm may have affected power. A medical issue may have changed the crew's condition. The ascent vehicle has to work not in a clean fantasy version of Mars, but after the mission has lived with the real planet. And when the time comes, there may not be room for delay. Orbital mechanics decides when the crew can come home. Mars and Earth keep moving around the Sun. A return window is not available every morning like a train schedule. If the mission is built around a particular departure period, missing that window could mean waiting much longer, with all the life support, supplies, health risks, and equipment aging that waiting would bring. On Earth, a scrubbed launch can often be reset. On Mars, a scrubbed departure could become a crisis. The ascent vehicle must be reliable after waiting. It must ignite when commanded. It must guide itself through the Martian sky. It must survive its own vibration and acceleration. It must place the crew on a path that allows rendezvous. The return vehicle must be where it is supposed to be. The navigation must be accurate. The crew has to transfer safely. Then the spacecraft has to leave Mars orbit and begin the journey back toward Earth. Only then does the final voyage begin. The return cruise is not a victory lap. It is another deep space mission, with radiation, isolation, limited supplies, and a crew that has already spent months away from Earth. The body that adapted to weightlessness, then partial Mars gravity, has to endure space again. Muscles and bones must hold up. Medical systems have to continue. Life support has to stay closed and reliable. The same distance that made rescue impossible on the way out still exists on the way home. Even Earth arrival is not simple. A spacecraft returning from Mars reaches Earth with enormous speed. The crew must survive re-entry, deceleration, heating, landing, and the physical transition back to one full gravity after a mission unlike anything human bodies have experienced. The moment Earth appears large in the window may feel like safety, but the mission is not over until the crew is actually down, alive, and recovering. That is why saying we can land robots, so we can land humans, misses the heart of the problem. A robot can be brave because it does not know it is alone. It can be sent without a return plan. It can die on the surface and still be considered a successful mission if it worked long enough. A human crew carries a moral obligation from the moment the mission is designed. They must have a credible way home. The return ticket is not optional equipment. It is the reason the mission is allowed to exist. That scenario is why the ascent vehicle carries so much emotional weight. It is not just another machine. It is the promise that Mars is a destination, not a prison. It is the bridge between exploration and survival. It is the proof that the mission still has a path back to the planet where every human life began. Getting humans to Mars is not one achievement. It is a chain of achievements performed in the right order, across millions of miles, with people inside the system the entire time. A rocket from Earth is only the first launch. Mars requires another. The crew has to escape two worlds, not one. That is the part the imagination often skips. We picture the first footprint, the flag, the red dust on a boot, the view across a cold desert beneath a pink sky. Those images matter. They are part of why Mars calls to us. But every footprint on Mars carries a question behind it. How do they get back? Until that answer is not only imagined, but tested, built, powered, fueled, landed, protected, and trusted, humans will remain just outside the story they want to enter. And once the return ticket is understood, the final answer to the title becomes clearer. Mars is not waiting because of a single unsolved mystery. It is waiting because every system has to succeed together. The launch, the cruise, the landing, the habitat, the resources, the crew, the ascent, the rendezvous, and the journey home. One missing link is enough to stop the whole chain. That is where the final part of the story has to go. Not to one obstacle, but to the real reason we are still waiting. The reason Mars remains so close in our imagination, and still so distant in practice. And that is the real answer hidden inside the question. Humans have not reached Mars because one missing invention has been holding the whole dream back. It is not just the distance. It is not only radiation, or landing, or fuel, or the human body, or the silence between Earth and Mars. It is all at once. That is what makes Mars different from almost every earlier step in exploration. A mission to Mars is not one machine leaving Earth. It is an entire chain of machines, people, supplies, habitats, power systems, medical plans, landing systems, communication networks, and return vehicles, all depending on each other across distance where help cannot arrive fast. If one link fails, the others may not matter. A perfect launch does not save a crew from a failed landing. A perfect landing does not help if the habitat cannot keep pressure. A working habitat is not enough if oxygen production fails, if power drops, if radiation exposure climbs too high, or if the ascent vehicle cannot leave the surface. This is why Mars is not simply the next moon. The moon was dangerous. Every Apollo landing was a risk, but it was close enough to remain inside the logic of Earth. Radio messages arrived almost instantly. A crew could reach lunar orbit in a few days. Mission control could help in real time. If something went wrong, the problem was still close enough to fight within human time. Mars changes the meaning of distance. A crew heading there is not taking a short trip away from Earth. They are entering a mission where Earth becomes a point of light, and the spacecraft becomes the only working world they have. For months, the crew must live inside a sealed system, while radiation passes through deep space outside the walls. Their bodies change under weightlessness. Their supplies slowly become more precious. Their psychology becomes part of the engineering. Then, Mars itself does not welcome them. It offers a thin carbon dioxide atmosphere, too little pressure for human life, no breathable air, no open liquid water on the surface, global dust, cold, radiation, and ground chemistry that still has to be treated with care. The planet looks like a destination, but for a human body, it is almost another kind of vacuum. The suit, the habitat, and the rover are not accessories. Each one is part of a temporary life support bubble, placed on a planet that will not forgive casual mistakes. That is the difference between visiting Mars in imagination and standing on it in reality. In imagination, Mars is a red landscape. In reality, it is a place where every breath is manufactured, every watt of power matters, every seal is important, and every repair may decide whether the crew can continue. Robots can accept this world in ways humans cannot. A rover does not need to keep its bones strong, protect its immune system, manage fear, treat an infection, or return to Earth after the mission is over. If a rover dies, the mission is tragic and expensive. But no family is waiting for a human voice that will never come home. That is why robots arrived first, and why they will continue to go before us. They are scouts. They map landing sites, test soil, measure radiation, search for water-related minerals, and study ancient riverbeds and lake deposits. They teach us where a human crew might land, where resources might be found, and where danger may be hiding in the terrain. Every rover track is a small preparation for a footprint, but a footprint is heavier than a wheel mark in every possible way. A human mission carries responsibility that a robotic mission does not. The life support system cannot merely work during a demonstration. It has to keep working while dust gathers, equipment ages, filters clog, seals wear, and astronauts are too far from Earth for a replacement part to be sent quickly. Mars demands durability. Not the durability of a machine tested for a day. The durability of a small world expected to keep people alive. That is why the moon still matters. It is not a distraction from Mars. It is a place to test some of the skills without the full distance penalty. Habitats, suits, rovers, power systems, partial gravity operations, dust control, and deep space habits while still being close enough for a much faster return. Mars is the exam. The moon is part of the training. Even then, the final step will be unlike anything humans have done before. A Mars crew must leave Earth knowing that the safest place in the universe is shrinking behind them. They must travel through deep space, land with precision, operate on the surface, maintain their own shelter, manage emergencies with delayed communication, perhaps use local resources, launch from another planet, rendezvous in Mars orbit, return through deep space, and survive re-entry at Earth. That is the full mission. Not Earth to Mars, Earth to Mars to Earth. The return is what turns exploration into a complete promise. Without it, the mission becomes something else entirely. A one-way human landing may sound dramatic to some people, but it is not the responsible architecture most agencies are trying to build. The real goal is not to prove that humans can be abandoned on another planet. It is to prove that humans can go, work, learn, and come home. Coming home is not an emotional detail. It is one of the central engineering requirements. That return requirement reaches backward into every earlier decision. The crew needs fuel, or a plan to make fuel. They need an ascent vehicle waiting or delivered. They need power to keep systems ready. They need vehicles in the right place at the right time. Mars is full of dependencies. A thing needed at the end may have to be prepared before the beginning. Cargo may need to arrive before the crew. Habitats may need to be checked. Supplies may need to be positioned. Power systems may need to start working before anyone lands. Oxygen and fuel production may need to prove itself before astronauts risk their lives on the surface. The first human Mars landing may depend on machines that arrive there years earlier. Those machines would be silent promises. A power unit running before the crew. A habitat already sealed. A cache of supplies already stored. A return system already prepared. A human mission begins long before the humans launch. That is why the question, why have we not reached Mars, can sound simpler than it is. It can make the delay look like hesitation, when much of it is caution forced by physics. The distance is real. The radiation is real. The landing mass is real. The biology is real. The need for return is real. Ambition does not remove those problems. It only gives people a reason to solve them. And we are solving them, piece by piece. Life support systems improve. Rovers map more of the planet. Satellites refine our understanding from orbit. Experiments like MOXIE show that oxygen can be made from the Martian atmosphere at small scale. Human spaceflight research studies radiation, isolation, medical risk, and altered gravity. New rockets and mission architectures continue to evolve. None of this means the first crew is already safe. It means the problem is becoming more defined. That is progress. Sometimes progress in space does not look like a dramatic launch. It looks like removing one unknown from a list, learning how dust behaves, measuring radiation more carefully, testing a seal, closing a life support loop, making oxygen from carbon dioxide, understanding how crews make decisions after months of isolation. The public often sees the rocket. The mission depends on everything behind it. Mars will not be reached by a rocket alone. It will be reached by thousands of quieter solutions working together at the same time. Human Mars exploration is not delayed because people stop dreaming. It is delayed because the dream has become detailed. A vague dream can ignore radiation, landing mass, communication delay, and return fuel. A real mission has to write them into the plan. The closer we get, the less simple Mars becomes. That does not make the dream smaller. it makes it more serious. Because Mars is worth seriousness. It is not only a red backdrop for human ambition, it is a world with a history. Once, water moved across its surface. River valleys, lake beds, minerals formed in water, and ancient terrains all suggest a planet that was once very different from the cold desert we see now. If life ever began there, even briefly, Mars may hold one of the most important answers in science. Did life appear twice in one solar system? Or is Earth the only world here where chemistry crossed that line? A human mission could explore with a flexibility no rover has. Astronauts could choose samples in real time, notice unusual rocks, repair equipment, drill, climb, improvise, and investigate complex terrain with human judgment. Mars is possible enough to tempt us and hard enough to humble us. One day, if humans do reach the surface, the moment may look simple in the footage. A boot lowers, dust shifts. A person stands upright under a pinkish sky. The horizon curves gently. The suit reflects the sun. A voice says something prepared, or maybe something small and human that nobody planned. But behind that, one step will be centuries of astronomy, decades of robotic missions, years of engineering, and a chain of systems that all had to work. The step will look quiet. The achievement will not be quiet at all. It will mean that humans crossed interplanetary space, protected themselves from radiation, kept their bodies functional, landed a heavy vehicle on a difficult world, survived a frozen desert, operated without real-time help, and preserved a path home. It will mean Mars did not become easy. It will mean we became careful enough. Humans still have not reached Mars because Mars is not waiting behind one locked door. It is waiting behind many doors, and every one of them opens into another problem. Some are engineering problems, some are medical, some are psychological, some are orbital, some belong to dust, radiation, atmosphere, fuel, or time. To reach Mars, we do not have to defeat one monster. We have to build a working chain across millions of miles, and when that chain is strong enough, the first humans will go. Not because Mars became safe, because we learned how to survive it. Until then, the red planet will remain where it has always been, close enough to shine in our sky, far enough to challenge everything we know about leaving home. Thank you for watching this journey through the real reasons humans still have not reached Mars. If you enjoyed it, leave a like, subscribe for more calm space documentaries, and write in the comments what part of the universe you want us to explore next. Wherever you are watching from, and whatever time it is there right now, I hope the night feels a little larger, and Mars feels a little more real. Good night.